Hi, in this video we are going to discuss about frequency response of an LTI system, and we'll be seeing the transient response and the steady state response. Okay, so what is an LTI system? It can be characterized with HE to the power j omega, which is the transfer of which is the DTFT of my Hn, means my impulse response. Now, frequency response means my input is a pure sinusoid, and we know that a pure sinusoid is an eigenfunction of an LTI system. So, but in real world scenario, in real cases, in the real world, we have a finite start time of any signal. Like, we cannot have a signal which is always on at all the time. It is always a finite start time. I turn it on and then it starts flowing into the system. So for this particular signal, for this finite start time signal, a signal of pure frequency but finite start time, what will be the response of my LTI system? So as you might know from other studies in signal processing also, that you always have some transient response which slowly dies out, and then there is a steady state response which you already have seen, which is the eigenfunction. So it will be a multiple of this, a scaled version of this, and with a phase delay. So basically that's what we are interested in finding out, what is the transient response because of this finite start time. So we have, let's compute, start from the first principles. Yn is the convolution of Hn and Xn, and plugging in the values. Now my Xn is simply this term, and this is basically h of m times x of n minus m, with the summation m goes from minus infinity to plus infinity. Like, this is the general formula, and I want to now solve it for the transient response. Okay, let's simplify the term. You know that this term basically is equal to 0 for all m greater than n. So basically your limits will change. Earlier your limit were minus infinity to plus infinity, but now you know that after n everything is 0, so my limits are only from minus infinity to plus n. And now okay, I can for all these terms, this is basically 1, so I can just get rid of this term. Now see, this term is basically this. You have got the summation from minus infinity to plus infinity, which was your original intention, right? Which was your original steady state response of LTI system. But then there is this term, which is basically from n plus 1 to infinity. We have to subtract these terms from here, which basically means that this is my transient response. So if you simplify this, you see this is my h e to the power j omega naught times e to the power j omega naught n. This is my steady state response, which you have seen. This is my complex scaling, and this is the term which is my transient response. So this is the thing. Now you see, as your n is increasing, this term becomes smaller and smaller, because summation is only from n plus 1 to infinity. So this is the steady state part. This is steady state part, and this is my transient part, transient response. Okay, now let's summarize. So we have my input as a finite start time, and then this is my steady state response, and this is my transient response. Now let's see, for a finite impulse response system, which means when my h of n is a finite signal, then my transient response will be 0 when your what do you say, n is greater than capital N. Like let's say if my h of m has a length of capital N, then as soon as I hit capital N here, everything will become 0 here. So transient response will die out essentially. This is for finite impulse response systems. But if we have an infinite impulse response system, which essentially means my h of m never dies down, never dies out, it just is non-zero for almost all future times, then, but if it is stable means you have read it in the DTFT definition and properties that it is stable when the signal is absolutely summable. When this is absolutely summable, then my system is bounded input, bounded output stable, BIBO stability. And so basically this means that my transient response will die out asymptotically. It may not die out immediately, but over a long capital N, it will die out asymptotically. Now, let's take an example. So that was the basic theory, but now let's see an example. So we have got, this is the system. Let us take a moving average filter. So what is the y of n for a moving average filter? So we have my y of n is 1 upon m and sum over previous m minus 1 terms. That is what is a moving average filter. But now, how do you find the impulse response of this system? So the answer is just input an impulse and see what is the response. So let us say my x of n is an impulse signal. So what is my y of n? That will be corresponding impulse response. So my y of n or h of n is 1 upon m summation over m equal to 0 to capital M minus 1. Instead of x, I will write delta. That's it. So this is my impulse response of this LTI system. Now, but this is in the time domain. What is it in the transform domain? So to find the frequency response, which is h e to the power j omega, what will I do? Just take a DTFT. That's it. So this is the formula for a DTFT, right? And now let us plug in the value of Hn. What does it become? So it is basically this term. This is my h of n and times e to the minus j omega n. Now you know how to deal with delta function. Delta will be 1 when n is equal to m. So let's eliminate n, which is going over a big range. Let's eliminate it and replace it with m. So this is what I get, right? Now this term looks very simple term, but to see the physical significance, let's simplify it further, or basically represent it in terms of something easy to understand. So we have basically, what we can do is, this is a geometric progression, and what is the sum of a GP? It is this: 1 minus common ratio power number of terms divided by 1 minus common ratio. That's it. And this is simply the sum of a GP. Now we can simplify it even further. You know, what is, if I take out e to the power minus j omega m by 2, if I take that as common, so this term will become e to the power j omega m by 2, and this is e to the power minus j omega m by 2. So basically this is the sinusoid. So I get 1 upon m, and this is the common term. So this is the common term which I get from here, and then the remaining is the sinusoid, and then similarly here the common is minus j omega by 2 and the sinusoid. So this is the thing, and now let's put it in a simple form, and that's the thing. Yeah, this is the form finally which we get. This looks very nice form. Basically, this is just a phase term. We can ignore it for our magnitude part. Magnitude part is simply sine of omega m by 2 divided by sine omega by 2, and some scaling 1 upon m, which is independent of omega basically. So let us plot it. Okay, this is what is my system. I just wrote the same equation which we derived. Now if I plot this, then how does it look like? So see, this is my magnitude response or my gain. You can see for when omega is close to 0, you can apply L'Hopital's rule and see sine and sine. Sine omega m upon 2 is approximately equal to omega m upon 2 when omega goes to 0. And this is basically omega cancel, it is just m and m cancel, so it's 1. So that's what I see here. The x-axis, at omega equal to 0, the gain is almost 1. And as the omega increases, my gain is dropping. And then there are some side lobes here. So basically what it means that if I am passing a pure sinusoid here, a real sinusoid, the output will be, if the frequency is close to 0, then the output is almost 1. But as the frequency is increasing, my output is dropping. My output will be scaled to a lower and lower values like this. And the frequency response, the phase response is something like this. May not make much sense, but yeah, this is the most important part. So what do I see here? That this allows the low frequencies to pass, right? You see the frequency from 0 to, let's say, something 0.1. It has got high gain, but for high frequencies, they are almost attenuated. Attenuated means they are suppressed. So in a way, this is a low pass filter. It is passing the low frequencies and cutting down the high frequencies. And you also know it from your intuition that a moving average filter is used for smoothing out the signals. So it is a low pass filter. But here we can see it in the frequency domain, that how low frequencies are allowed to pass and the high frequencies are curtailed. So this is what was frequency response, and we saw transient and steady state response in this lecture. Thank you.